Hi, this is Professor Fernandez, and in this video, we're going to work out an example of using a Taylor polynomial to approximate the value of a function. This example comes from the notes from lesson 14. You can find those notes on this website along with these other resources. The first thing I'm going to do is to remind you of Taylor's theorem. I'm going to zoom in here on the lower right-hand side. This is from the notes from lesson 14. And so ignore this giant thing in a minute. That's actually what we're going to use to solve the example, but that comes from Taylor's theorem. So let's read Taylor's theorem. It says, let I be an interval containing C. C here, remember, is related to the Taylor polynomial. So if you are needing a little refresher on Taylor polynomials, take a look at video 13.2 or also video 13.1 in this series where I work out the Taylor and Maclaurin polynomials. Anyway, so C is the C from a Taylor polynomial. You say, oh, find the Taylor polynomial of f of x about c equals 7, right? That's the C we're talking about here. Okay, so I is an interval containing C. So, think of, for all visual purposes, C here, and then I is maybe some interval that contains C. That's I. Let f be differentiable up to order n plus 1 on I. Very similar to the requirement for calculating a Taylor and Maclaurin polynomial. The function is differentiable enough times. Denote by t sub n the nth Taylor polynomial of f at c. Okay, those are all the assumptions. So here are the starts of the conclusion. Then, for each x in I, so if I pick any point here, any x in that I interval, there exists a z, okay, between x and c. Okay, so here was my x, here was my c. In this case, z would be in here, right? So z would be in there. Z is in here. Such that what? Such that, so here's the kicker. This is a really interesting result, and this is why it's called Taylor's theorem. The value of the function at x, f of x, is equal to the value of the Taylor polynomial, nth Taylor polynomial at x, t sub n of x, plus this other stuff. Okay, a couple of things to say. First of all, this is really amazing because the function could be some very non-polynomial function. Could be a transcendental function. It could be, a sine, cos, e to the x, ln, whatever. T sub n of x is a Taylor polynomial. It's a polynomial. X squared plus x cubed plus x to the 19th, whatever, right? So Taylor's theorem, what it's telling us is that f of x, whatever type of crazy function it might be, there are a bunch of hypotheses. It has to be differentiable enough, but still, could be e to the x, could be cosine x, can be written as the sum of a polynomial plus this term. And this is a single term, even though it looks pretty complex. Let's dive into it. So, that first takeaway, the function, as long as it's differentiable enough, is a polynomial plus a term. And what is this term? Two things to say about this term. If you remember the Taylor polynomial, t sub n of x, it's f of c plus f prime of c plus times x minus c plus all the way, the last term in the Taylor polynomial is nth derivative evaluated at c over n factorial x minus c to the n. If we were to write out the next term here, this would have an n plus 1, this would have an n plus 1, this would have an n plus 1. Hey, that's this, this, and this, right? So this term that gets added to the Taylor polynomial and therefore gives you, equals the function, right? This term is almost the next term, which would have been over here in the nth Taylor polynomial. It's almost the next term. What is different? The next term over here would have had n plus 1 derivative evaluated at c over n plus 1 factorial. Whereas over here we have n plus 1 derivative evaluated at z. Remember, that's why I kept drawing this little diagram. Z is between x and c. So it's not necessarily equal to x. It could actually be equal to x in some cases. It could be equal to c in other cases, but it's in between in general. Okay, so that's a lot to throw at you, I know. But the good thing is that this is a video, so you can rewind it, all right, and hear it over and over again and try to digest it. So next thing I'm going to do is give you one application of this really remarkable result, and then we'll talk about the example, and I'll illustrate all the things we talked about with that example. One application of what's going on here, right? Let's pop this out here. f of x equals nth Taylor polynomial at x plus this additional term here, which, like we just saw, is almost the next term in the Taylor polynomial, just that instead of nth derivative at x equals c, it's nth derivative at z, n plus 1, sorry. Now let's do some algebra here, right? Let me subtract t sub n of x from both sides. That gets me here. See if I can just duplicate that, save ourselves some time. Duplicate, yes, great. Okay, and then now I'm going to take the absolute value of both sides. Absolute value here, absolute value there. Okay, this turns into absolute value of n plus 1 derivative evaluated at z. N plus 1 factorial, n here is always a whole number, so that's just never negative. And then over here we have x minus c absolute value to the n plus 1. Okay, this thing over here is what we're going to work on in a minute. Before we do that, let me just show you and discuss why I'm doing this. The thing on the left-hand side is the difference between the value of the function at x, f of x, and the value of its Taylor polynomial at x, t sub n of x. And we're taking absolute values of that difference. So we're measuring the magnitude of the difference. You know, maybe f of x is 1 and t sub n of x is 0.9. So f of x is bigger than t sub n of x, the difference is positive. Maybe f of x is 0.2 and t sub n of x is 1. So that difference is negative. So by taking the absolute values, we're focusing just on the magnitude of the difference, not whether it's, you know, positive or negative. In other words, whether this is bigger or whether that is bigger. Okay, Taylor's theorem then tells us that the magnitude of that difference is equal to this term. This is pretty remarkable. This is another way of seeing Taylor's theorem, right? It tells us that if you have a function which is differentiable enough, and you look at a specific x value, you calculate the output f of x, the difference between f of x and t sub n of x in magnitude, right, is exactly equal to this. Pretty amazing. You know, there's a subtlety here. What Taylor's theorem actually says is that, going back to the conclusion, there exists a z such that this statement is true, that magnitude difference is equal to this right-hand side term. Subtle difference, but for us, how we're going to use it here is we're going to use it to bound the error in approximating the function's value with the value of its Taylor polynomial. What do I mean by bound the error? Okay, let me just move this over a little bit so we can work on it. Move it over here. Okay, so we don't know anything about z, right? All we know is that there exists a z, and it's between x and c. Remember the picture I drew? Here is c, right? There was an interval I, and then x was inside this interval, and then z was between, somewhere here, between x and z, x and c. Okay, so that's kind of all we know about z. But what if we now assume that I can find the maximum of the nth plus 1 derivative of x over the interval x to c? Okay, then I would say that this entire thing is less than or equal to the maximum of the absolute value of the nth plus 1 derivative of x over the interval. You know, it could be x less than or equal to z less than or equal to c. This is if c is bigger than x, or it could have to be the other way around, right? This is if x is bigger than c, right? Either way, if we do manage to find this maximum, right, whichever one of these intervals works, then it really is greater than or equal to whatever the nth plus 1 derivative of f evaluated z could be, right? So divided by n plus 1 factorial times absolute value of x minus 1 to the n plus 1. This, however crazy it looks, and I will show you in a minute how to actually use this in practice, is in fact a way to bound the difference between f of x and t sub n of x. Because again, we're saying that difference in magnitude is now at most this thing. And I know part of you is saying, whoa, I have no idea how to make sense of that thing. And again, that's what we'll do in about 30 seconds with the example. Last thing I'll say is that, you know, I'll use u sub n plus 1 for the maximum of the absolute value of the nth derivative of the function f over, whatever the correct interval is, x to c or c to x. Okay, I'm just going to use u sub n of x for that. And then that explains why I had, put this here, this inequality here, and why also earlier I said, let's just ignore that for now. I'll get to that. Okay, so if I had to summarize what I just said in perhaps the simplest way possible, I would say this inequality, what it does is on the left-hand side, you have the absolute value of the difference between the value of the function and the value of the Taylor polynomial, right? So this is like the difference in the actual number minus your approximation. So you can think of the left-hand side as the absolute value of the error in approximating f of x by t sub n of x. And this says that the error is less than or equal to this particular thing, which has a lot in it. But the point is that we therefore, if we can calculate it, we can therefore say, oh, the error is at most this. So we can bound the error. So that's what's going on. Okay, let's see that for an example over here. So what does it say? It says, what degree Maclaurin polynomial guarantees that the error in approximating sine 1 by mn1 is at most 0.1? Okay. So again, let's go back to this and write out this inequality. So here, sine of 1 is the f of x at x equals 1 value, right? We're trying to approximate the output sine of 1. We're trying to approximate that by the nth degree Maclaurin polynomial of sine of x, the function here, at x equals 1. So that's mn of 1. So we're doing, this is the f of 1. We're doing minus mn of 1, right? This is the mn of 1. We're going to take the absolute value because we don't really care if our approximation is an overestimate or an underestimate, positive or negative difference. Okay. And then going back to this inequality here, we're going to say this is less than or equal to u sub n plus 1, right? Remember that was the maximum of that n plus 1 derivative, divided by n plus 1 factorial, times absolute value of, it would have been, I'm just kind of rewriting down here, it would have been x minus c to the n plus 1. We know x and we know c. How do we know that? First of all, Maclaurin. Remember, a Maclaurin polynomial tells you that c equals 0. So we know that c is 0. And then x. What is x, right? This over here would have been f of x minus mn of x, just as it was over here. X here in this problem is 1. So I'm going to go over here to the right, and I'm going to put in a 1 right there. So the thing that goes up here is 1 minus 0 to the n plus 1. Let me pause for a minute, right, and just keep the screen here. Notice that we just did a lot of really critical reading of the assumptions and really latched onto every word. Maclaurin, that means that c equals 0. That allowed us to put a 0 here. Mn of 1, right? 1 is where the x would be down here. So that allowed us to put a 1 over here, right? So I really do encourage you, and this is one of the skills that math helps you with, which is to be very precise in both your reading and how you write down mathematical results or calculations, right? And it's really useful here. The last thing I'll mention is we are looking for the degree. Again, latching onto that, very critical reading. The degree. Are we looking at a third degree polynomial, Maclaurin polynomial, and that will guarantee this error? We're looking at an 11th degree, right? That is an n value. Because remember, n in m sub n over here is about the degree of the polynomial. Okay, so one thing we haven't done, we have yet to talk about how do we put in this 0.1. Well, again, this is the absolute value of the error in approximating sine of 1 by the nth degree Maclaurin polynomial evaluated at x equals 1. That's the error. That's the value of the error. And we're saying it's at most this thing. If we can find a way to get this thing to be less than or equal to 0.1, you can see already that if we then are able to solve for n again is the degree that will give us the answer, right? If we now work on this inequality and solve for n, we might get something like n equals 7, and then there we go. Use a 7th degree Maclaurin polynomial. That'll get your error down to at most 0.1. We might get something like n bigger than or equal to 13. We might get an inequality for n, right? Those are some of the options or possibilities that might happen. Okay, so we're almost there to being able to answer this question. The next thing we're going to do is work on this part. So anytime you answer questions of this form, what's the degree of the Taylor or Maclaurin polynomial that you need to get the error down to at most blah, you're going to end up using this inequality down here, right? And to use that, you are going to have to work out this part. So remember, u sub n plus 1 is the maximum of the absolute value of the nth plus 1 derivative of the function over either the interval x to c or c to x, okay? Depending on where x and c are relative to each other. So let's work that out for this example. So here, the function that we're dealing with is sine x. Okay, and if we start taking derivatives, because we want to look at the nth plus 1 derivative, the nth derivative of sine x is going to be plus or minus sine x or cosine x. Okay, if we take derivative of sine, we get cosine, we get derivative of cosine, that's negative sine. They kind of go back and forth, and then they alternate with the plus or minus, potentially. So does it matter that this is nth derivative that's n plus 1? No, it doesn't really matter, because again, all the derivatives of sine are either sine, cosine, or plus sine, or minus cosine. So when I take the absolute value over here, right? So I'm going to take the absolute value of these things. These potentially negative signs go away. So now we're talking about just absolute value of sine x or cosine x. And we want to then talk about the maximum. Technically, we want to talk about the maximum over these intervals. But in this particular example, we don't have to worry about the interval, because if we think about the graphs of sine x and the graphs of cosine x, we know that the maximum that they will ever be, not even thinking about the absolute value of these graphs, is 1, right? That's the amplitude of sine and cosine. So sine or cosine in absolute value is always less than or equal to 1. That is our u sub n plus 1. That is our maximum of the absolute value of the n plus 1 derivative of the function in this example. So 1, right? That's one of the reasons I chose this example. We've done enough complex stuff already that's choosing an example where u sub n plus 1 works out quite nicely. Really helps us to take a little brain break. Okay, so over here, we go back here and we actually have our u sub n plus 1 now is equal to 1. That's very nice. So if I write out this inequality, first of all, 1 minus 0 is 1. Raised to the n plus 1, that's just 1. So this inequality is 1 over n plus 1 factorial less than or equal to 0.1. That has simplified considerably. 0.1 is 1/10. So now I can just take the reciprocal of both sides. Gives me n plus 1 factorial bigger than or equal to 10. And, factorials are, tricky to work with if you want to solve an equation or inequality involving a factorial. It's not like, we're used to doing with, I don't know, a quadratic formula or just, regular algebra. So I recommend making tables if you run into this. Usually, hopefully your instructor's nice and, the answer ends up being a small n factorial. So here is n plus 1 factorial. We're looking for the first time that n plus 1 factorial gets bigger than or equal to 10. So let's just start with, 2. So 2 plus 1 factorial, that's 3 factorial. That's 3 times 2, that's 6. Doesn't meet the criteria, not bigger than or equal to 10. Go to the next one. 3 plus 1 factorial, that's 4 factorial. That's 4 times 3 factorial, so it's 4 times 6, that's 24. There we go. That is definitely bigger than or equal to 10. And then, of course, if I choose a bigger factorial, bigger n, because of the way factorials work, this would be 4 plus 1 factorial, that's 5 factorial. That's bigger than 4 factorial. So 24 is the first one in this list that's bigger than or equal to 10. That happens at n equals 3. So I'll erase this and then write out the conclusion, which is that if we're looking for an n value such that n plus 1 factorial is bigger than or equal to 10, n bigger than or equal to 3 is what we're looking for. So how would we then express this as the answer? We would say, well, we were looking for the degree Maclaurin polynomial that guarantees blah, blah, blah. Well, now we have an answer. At most, at least 3, right? N bigger than or equal to 3, at least 3. Okay, so that would be the answer. You could just write n greater than or equal to 3. Hopefully your instructor would say, great, that's actually true. And that would be it. One thing I want to do just to illustrate what we did here. Right, let's actually write out the third degree Maclaurin polynomial and evaluate it at 1 and compare the numerical outputs to each other. So M3 of 1, first let me remind you what M3 of x is. Remember the Maclaurin polynomial for sine x. We, I think, calculated this in video 12.1, 13.1, one of those. Take a look at the previous videos in the series. This is x minus x cubed over 3 factorial. So if I substitute in 1 for x, I get 1 minus 1 over 3 factorial. This is 1 minus 1 6. This is 5 6. I took the liberty of looking up the decimal for this because it'll be important when we compare in a minute. It's 0.8333. Okay, if we write out now sine of 1, we're looking at here radians, always in radians in calculus. This ends up being 0.841 dot dot dot. So when we look at the difference that we were working with here, sine of 1, the actual value, minus the third degree Maclaurin polynomial of sine of x evaluated x equals 1, that's what this is. Now we're calculating this difference, 0.841 minus 0.833, and that ends up being, let's see, 0.0081 dot dot dot. So again, you can see that this number is definitely less than or equal to 0.1. It's actually like quite, orders of magnitude less. So in other words, we have achieved much more than we set out to do. We've shown that you can approximate sine of 1, which is this number, with the third degree Maclaurin polynomial of sine of x, evaluated x equals 1, which is this number. And that approximation is pretty accurate, right? It's off by this much. It's accurate to 2 decimal places. It starts differing in the 3rd decimal place. Okay, so there was a lot in this video. I definitely recommend that you go back and take a look at it one more time. In some sense, this lesson is a capstone lesson. We are now not just dealing with Taylor polynomials. We are also now dealing with how they relate to the function itself. And we're also bringing back some concepts from Calculus 1 dealing with the maxima, extrema of functions, right? For more advanced examples of doing exactly what we did here, you may have to pull out some of that heavy-duty optimization theory, find the derivative, critical values, critical points, all that stuff. We didn't for this example. That's why I wanted to start off here, but I just did want to mention that. Thanks for watching.